All right. So previously, I guess I was saying we want to look at different types of work. I guess that's true, but really what we're trying to do initially is just look at different expressions of work. So let's have a look here at the first thing we want to look at is the work of a variable force. All right? So recall that you've got a force acting on a particle, and the particle is perhaps moving in a different direction. And so recall that in a differential sense, our differential work was F dot dr, or it was F ds cos theta. Okay? Now, if we want to take this term and get the total work, remember we just need to integrate, right? We need to integrate between R1 and R2, or if it's in scalar form, between S1 and S2. Okay? So I know I wrote this, perhaps I should have put the cos theta there, but you get the idea. That if we integrate this term over here, we're going to get this. The work from 1 to 2, time 1 to 2, is equal to this integral here, which is equal to that integral here. This is in vector form, that is in scalar form. Now, this is the most general way of expressing the work, meaning that from this expression here, you can solve any work problem. Okay? The following expressions for work are more specific to different types of situations. But if you know this, then if you understand how to apply this, you can apply this to any single problem. So this is, we keep both these terms, f and cos theta, inside the integral. Why would you want to ever keep a term inside an integral? It's if that term f, or the angle, is varying. Okay? If it's a function. And in this case, f needs to be a function of s, and theta needs to be a function of s. So if both f and theta are changing, right, as this particle is moving from S1 to S2, if both the magnitude of the force and the direction of the force is changing, okay, or rather the direction, the angle between these two vectors is changing, then we need to keep it inside the integral because it's the work of a variable force. Okay, now we're going to get more specific. If that force is constant and the angle between the force and the displacement is constant, then what do? We remove it out of the integral. So this is the work, this is number 2, the work of a constant force moving along a straight line. So both your force and the angle between the force and the displacement is constant. You take it out of the integral, and we are left with this equation. The work from 1 to 2 of a constant force along a straight line is simply this. It is the magnitude of that force times the cos of the angle times the displacement, S2 minus S1. Okay? So please pick that up, guys. U1 to 2 equal to F cos theta ds. That is the most general expression. If f and cos and theta are varying, you keep it inside. If f is varying and the angle is not, you bring the angle outside, cos theta out. If they're both constant, you bring both of them out to get this. Okay, we'll look at the work of a weight in the next video.